Bismillah ar-Rahman ar-Rahim. Assalamu alaikum everyone. Today we are at lecture number 22 and this is week 11. We are now starting a new chapter, chapter 7, which is series parallel circuits. So the circuits can be the combination of series and parallel circuits that we have seen. Series circuits we have seen in chapter 5 and parallel circuits we have seen in chapter 6, but in practical applications there could be circuits which have a combination of these two, that is there can be components which may be connected in either series or parallel or combination of series and parallels. These are the today's lesson contents. First of all, an introduction to series parallel circuits. Then we will see different approaches which would be implemented to solve the complex series parallel circuits and to find out the unknown quantities like voltage, current or power. These approaches are first of all general approach, then a reduce and a return approach, and block diagram approach that we will cover one by one in this lecture. So let me see what are series parallel circuits. So series parallel networks are networks that contain both series and parallel circuit configurations. A firm understanding of the basic principles is sufficient to begin an investigation of any single source DC or multi-sources connected only in a simple series or parallel network having a combination of series and parallel elements or branches. That means the only basic principles which we have learned till now would be sufficient to investigate and solve the circuits which are having a single source or multiple sources, and they are connected in any configurations parallel or the combination of series and parallel branches. So what is a general approach to tackle a particular series parallel network? These are the guidelines. So first of all, take a moment to study the problem in total. Draw an overall look at the circuit and make a brief mental sketch of the overall approach. इसमें आप सबसे पहले आप सर्किट को देखें कि कौन से कंपोनेंट्स जो है वो सीरीज में हैं, कौन से पैरेलल में हैं, एंड देन एक मेंटल स्केच आप डेवलप कर लें जिससे आप इस प्रॉब्लम को अप्रोच कर सकते हो इजीली. Then examine each region of the network independently before tying them together in series parallel combinations. That is, you break the complex circuit into segments and see which components are in series, which components are in parallel, and what is their combination. Then redraw the network as often as possible with the reduced branches towards source, keeping unknown quantities undistributed, or have a provision for the trip back to unknown quantities from the source. So what happens is for a complex network you are asked for certain unknown quantities. These unknown quantities would be indicated in the circuit, whether they are voltages or currents in a particular branch or a component. Then you have to find out those unknown quantities in the circuit. So for that you have to approach the circuit in a way that you try to reduce the circuit towards the source. So first of all, what you do is you redraw the network as often as possible. That is, in a simple structure, try to draw the circuit so that it is easily understandable and it is having often configuration. Then look for the unknown quantities that are required to be determined. This approach we will see in detail in the next slides. Now let we see how general approach is applied in a particular circuit. For that, this is the example circuit in which we want to apply this approach to find out these unknown quantities V1, V2 and I. In this circuit you can see that it is not clear about the combination of the series and parallel components. Few are quite obvious. For example, these two resistors are in series, but what about these two resistors R1 and R4? They are not in series with these resistors, rather they could be parallel with these two resistors. For example, this R1 and this battery would be parallel with R2 and R3, that we will see in our next step. So for that, first of all, we have developed a mental sketch of the problem and see the problem in total, that which components are in series and which are in parallel. So to some extent we have seen that few components are in series and the combination of the components with the other components are maybe in parallel. Then we next examine each region of the network independently. That we have seen that we break the circuit into regions, so that R2 and R4 were seems to be in series and the other combinations are there in parallel. So there are we have seen that this circuit has a combination of series and parallel components, and then we try to simplify the problem and see how can we redraw the network as often as possible. So this is very important step, that try to redraw the circuit to a form which is very obvious. So for this step to be implemented, first of all, what we do is we try to draw the circuit in a planar form, so that all the ground connections are set to a common point, and the batteries are indicated with the two terminals symbol, and then at these label nodes, the number of connections which are connected at this node are indicated in this way. As you can see that this is the node which is shaded in blue and has the maximum number of components connected. So this node is extended with a long connection, so that number of components can be shown in a planar way and a simple form. So first of all, you can see that at this node which components are connected. You can see that R3, R4, R1 and battery E1 negative terminal. So R3 again, R3, R4, R1 and E1 batteries negative terminal. So one of all these components are connected to this node A, which is shown here. Then the other terminals, you can see that the terminal of R3, other terminal of R3 is connected with R2 and they sits in series. So you can see that R3 and R2 are connected in series. Which terminals are connected with grounds. So you can see that I have indicated a ground wire or ground terminal which with a long straight connection in a planar way, so that many components can be connected with this ground. So first of all, R2, one terminal of R2 is connected with ground and second is connected with R3. Similarly, one connection of R4 is connected with node A and other is connected with ground. So R4 has one connection at node A and other at ground. Battery E1 negative terminal is connected with A and positive terminal is grounded. So positive terminal is grounded, so it is indicated here. Battery E2 has a positive terminal connected with R1, that is shown here, where the other terminal of R1 is connected with node A, and the ground terminal of the negative terminal of the battery E2 is connected with ground. So negative terminal is connected with ground. So this is how you redraw the arbitrary shaped circuit into a planar and often topology. So then label all these resistors and their values, associated values. E1 is of 6 volts, E2 is of 18 volts, and the unknown quantities that we are asked to determine are also indicated across the required components, that is voltage across R1 is V1, voltage across R4 is V2, so this resistor is R4 and voltage across this is V2 defined here. Similarly, current that is entering into the negative terminal of the battery are leaving the positive terminal of the battery. As you can see that this current I is also entering into the battery, and the current that would be leaving from the battery would also be entering into the battery. So this current I and this current I would be equal. So first of all, we have redrawn the circuit, and then by simple observation about voltage V2, this voltage is across this battery E1, so whatever the battery voltage is, that would also be voltage across R4, that is V2 would be equal to E1, but with polarity is opposite, so it would be negative. So V2 is equal to minus E1, and which is equal to minus 6 volts, because this negative terminal is connected with this point and positive is connected with this point, so voltage would here would be minus 6 volts with respect to ground. Then by KVL in the right loop, in this loop, we can always apply Kirchhoff voltage law to find out the unknown quantity in this loop, which is V1, and the rest of the quantities of the loop are known. That is, this voltage we know is 18 volts, this voltage we know is 6 volts, and this is the unknown. So by applying the KVL we can find out the unknown quantity V1. So V1 would be equal to E1 plus E2, which is 24 volts. Next is to find out the current. We can always apply Kirchhoff current law at a particular node. So at node A we can apply Kirchhoff current law. This is the node. So this current is I coming out of the node. This current I2 is entering into the node. This current I3 is also entering, and this current I1 which is labeled here is also mentioned the direction that you can see that the conventional current is always from the battery. The conventional current is always leaving the positive terminal of the battery and entering into the negative terminal. So direction of current I1 would be upward. The direction of I2 would be again you can see that the voltage at node A is negative, so current would always flow from higher potential to lower potential. So this is zero potential, and this is some negative potential. This is minus 6 volts. So this is minus 6 volts. So current would always flow from higher potential to lower potential. So I2 would actually flow upward. I3 would also flow upward, and so by applying KCL, sum of all the currents that are entering would be equal to currents leaving. So these three currents I1, I2 and I3 are entering into node A, and current I would be leaving node A. Now as we do not have the values of these currents, but we can find out the values of these currents by using Ohm's law, that I is equal to V by R. Value of current I1 would be equal to the current flowing through this resistance R1. By Ohm's law, the value of current would be V1 divided by R1. Then plus I2 would be equal to the voltage across resistor R4, which is E1, because this battery is connected exactly across this resistance R4, and the value of the potential is 6 volts. So 6 divided by 6 would be the current I2. So E1 by R4 would be current I2 plus I3 is current defined here, which is the value of current that flows through these two resistors. So the voltage across these two resistors is again E1 divided by sum of these two resistors, R2 plus R3 will give me the current through these two resistors. So by plugging these values, V1 is we have computed already in the previous slide, which is 24 volts, and R1 is 6 ohms, plus E1 by R4, which is 6. E1 is 6, R4 is also 6 ohms, plus the voltage across these two resistors would also be 6 volts divided by the sum of these two resistors, 7 plus 5, which is 12 ohms. So after computing these values, we will end up with the answer equal to 5.5 amperes that this current would be equal to 5.5 amperes, which was we are trying to compute using KCL. Next is the reduce and return approach. This process enables you to reduce the network to its simplest form across the source. So what you do is you try to reduce the circuit in a simplest way. Try to solve the components which are connected in series and parallel, and simplify the circuit that we will see later on the approach, so that all the resistors are then combined to an equivalent resistance, and that equivalent resistance at the source is used to determine the source current. In the return phase, you can use the resulting source current to work back to the desired unknown. So what you do is you reduce the circuit first into a single resistor and a single source, and then using Ohm's law find the current using voltage and resistance, and then use the value of this current to find out the unknown quantities. So this approach is more useful and viable in circuits which have single source. So for most single source series parallel networks, this approach provides a viable option towards the solution. So in some cases shortcuts can be applied that save some time and energy. So for example, at this top left corner you have a circuit with a single source, DC source applied, and circuit components which are connected in series and parallel. So they are combination of series and parallel configurations of the circuit. So what this approach says that you simplify this circuit and reduce the circuit into a single you reduce the circuit to its simple form across the source. So try to reduce the circuit into a simple form that you can see that across the source. So look at this blue shaded region. That blue shaded region, this was initially having a complex configuration that is further simplified into these resistors, and these resistors further simplified into the equivalent resistances, and then these equivalent resistances are further combined to form a simple single resistor. So this is the reduced phase. In this phase the circuit is reduced to a simpler circuit having one voltage source and one resistance. So if at this point, when you arrive at this point, you can find out the value of the source current by using this simple equation that IS would be equal to E divided by RT, where RT is the equivalent resistance of this whole or shaded region. How this resistance is computed? First of all, you see that you can combine these two resistors which are in series, so call it as R dash. So R dash would be equal to R3 plus R4. Then this R dash new resistance, which is the combination of these two series resistors, is appears in parallel with this R2. So solve these two resistors to form a single resistor that call it as RT dash, which is the parallel combination of R2 and R dash. So R2 and R dash in parallel, and then these two resistors form this single resistor, which now sits in series with resistor R1. So these two series resistors can be combined and resulted into total RT, which is equal to R1 plus RT dash. Then once you arrive at this stage, then you can find out total current IS, and by finding this current IS, and then to find out the voltage across this final resistor V4, how we would proceed uh, to from this point to find out this unknown voltage, that is called the return phase. So in return phase, you first as a first step, what you do, you come here and then follow this path as this. So this is the flow of the approach, starting from this point and following this path and end up with this stage to find out voltage V4. So what we do is, after finding out the so after finding the value of IS from this point, then we use this circuit to find out the voltage V2, as V2 would be equal to IS into RT dash. So after computing voltage V2, we are now at this point. So after finding voltage V2, we use this circuit to represent this value of V2 here. Which is indicated in the circuit. Then by knowing the potential at this point, then we move back. This is the return phase, so we move back and show the circuit in this form. So by showing this circuit in this form, you can see that this voltage V2, which is defined here, is basically would be divided into this resistance and this resistance. How much voltage would be across this, how much voltage would be across this. The voltage across this resistor we can find out using voltage divider, that R4 into V2 divided by R4 plus R3. So this is how you end up with the solution to find out the unknown quantity in a series parallel circuit containing single voltage source. So another example in which this current I3 is required in this series parallel combination circuit, that for that we can use the reduce and return approach. So you can see that first of all, in this example we want to In the next example, we want to apply the we want to apply the reduce and return approach to find out the unknown current I3. For that, to reduce the circuit into a simpler form towards the source, first of all, these two resistors would be in parallel. They can be combined to form this single resistor R dash. So the parallel combination of R2 and R3 is 4 kilo ohm. So this would be 4 kilo ohm. This becomes in series with this R1. So that R total would become R1 plus R dash, which is 2K plus 4K, 6 kilo ohm. Then IS would be E by RT, which is 54 divided by 6K, 9 milliampere. So this current would be 9 milliampere. Which is divided into this current and in this current. So if you know the total current, then you can use voltage divider formula to find out the desired current I3. So this is the current divider formula that we have learned in the previous classes. Using that current divider formula, you can find out the desired current. Next is example 7.2, in which we want to apply the reduce and return approach to find out the unknown quantities V2 across these two resistors and current I4. And in part B, you are asked to insert the meters to measure current I4 and voltage V2. So a DMM so a digital multimeter is used to measure the current and voltage. So this is the circuit in which we want to find out the voltage V2 and these two currents. So first of all, these two resistors are in parallel, so we can combine these two to form a single resistor. So R2 and R3 would be in parallel, so they can be solved to find a value of 1.8 kilo ohm, which would be in series with resistance R1. So from these two resistors in series, we can find out value of voltage V2 across this resistance using a voltage divider formula. As we know that voltage across these two resistors is E, which is 12 volts. So with voltage divider formula, we can find out V2 as R dash divided by R dash plus R1 into E, which is equal to 2.51 volts. So V2 would be equal to 2.151 volts. To find out I4, we can see that the I4 would be equal to voltage across R4 divided by R4. Voltage across R4 would be equal to E, that is R4 is exactly in parallel with this supply. So I4 would be equal to V4 divided by R4, RE by R4, which is 12 by 8.2 kilo ohm, 1.46 milliamperes. To find out value of IS, this is the third unknown which we want to find out. We can apply KCL, that IS would be equal to this current plus this current. This current is I4, this current, let we call it I1. So this current I1 would be equal to E by R total, which is sum of these two resistors. This I1 would be equal to 1.4 milliampere. IS would be equal to I1 plus I4, which is 2.86 milliampere. Then in part B we are required to insert the DMM to find out the uh, desired to measure the desired quantities, that is V2 and I4. So to measure the V2 using DMM, we can apply the DMM leads across these resistors, that is a positive terminal of the meter is connected with the positive side of the positive polarity of V2 and negative is connected with the negative side, and this value of the meter will show me the voltage V2. And to measure the current, we have to break the circuit and insert the meter between these two terminals to find out the value of I4. And total IS can be seen here, that is coming from the battery terminal, that is 2.86 milliampere of a 12 volt source. So for a 12 volt source, 2.86 milliampere would be the IS current. So this is the 12 volt source, and the current IS that would be established from the source is 2.86 milliamperes. Next is the block diagram approach. That we will cover in the next class, inshallah. Thank you. Allah Hafiz.